Hi everyone, welcome to today's topic. So this is my topic number 19, and for topic number 19 I have chosen metal carbonyl. This is a important topic from organometallic chemistry. I have previously uploaded one video from organometallic chemistry that was the basics of organometallic chemistry and the 18 electron rule. Okay, so we know that what is actually organometallic chemistry, where the metal and carbon bond is present. So among the organometallic compounds, metal carbonyl actually is a important compound. Okay, so in this video we will be talking about some important factors or some important features of metal carbonyls, how they are bonding with metal, the how the bonding of carbonyl with metal actually affects in many ways. Okay, so that we will discuss. So let's start with today's topic, and also for from the CSIR-NET point of view, this is a very important topic. So keep patience and watch this video carefully. Okay, so let's start. So this we know, right? What is organometallic compound? Organometallic compound is, we know, metal carbon bond is present, right? So now we will be studying what is actually the metal carbonyl. What are metal carbonyl? Where M and CO bond is present. Okay. In a complex, we know complex are, we represent inside third bracket, right? Metal should be here. Any metal can be 3D or 4D series metal can be there. The transition metals can be there, and here we represent ligands. So let's say for octahedral case, so let's say six ligands are there. So among six ligands, one should be carbonyl. That time we can say that this is a metal carbonyl compound. Fine. So carbonyl, I have told you previously also, and you know also that carbonyl is a what type of ligand? It is a pi acceptor type of ligand. I have told you that when I was teaching, I think, coordination chemistry or the basics of organometallic chemistry in that part. Okay. So if you have not watched that video, please watch that first. So this is a pi acceptor kind of ligand. What is that mean? So every ligand first donates its electron to sigma bonding. So every ligand are first sigma donor, and for the case of carbonyl, it first donates sigma through sigma bonding, obviously, and then it accepts pi electrons from metal. So it is a sigma donor and pi acceptor ligand. Fine. So there are two types of actually metal carbonyl, two kind of metal carbonyl we can see: homoleptic and heteroleptic. With one example only, you can understand this fact that homoleptic means only carbonyl will be the ligand of that complex. Okay, then it will be called homoleptic. And for the heteroleptic means that uh, some of the among the six ligands, some of them are carbonyl, but there are other ligands also present. That time we will call it heteroleptic carbonyl, metal carbonyl complex. Okay, so this is simple. Now the bonding in metal carbonyl. I have previously told you that first it will donate via sigma bonding, and then metal will donate electron from its d electron actually. The metal will donate its d electron to the pi star of the carbon. Okay, let's just see what will happen. So here we know that carbon. What is the structure of carbonyl? C O. It will be plus and it will be minus. So first it will donate via this negative charge to the metal. Okay, and then metal has its d electrons. Okay, and it has what? Carbonyl has it has pi bonds, right? So it has pi star, vacant pi star orbital. Okay. So now metal d electron, if metal has a higher electron density, it can easily donate electron to its pi star orbital. Pi star means we can write like this way. This will be positive, then this will be positive. Like that way. So it can donate to pi star orbital. Okay, fine. So due to this donation, okay, the fact is that first sigma bond will form, then pi bond will form through the back donation from the metal. Okay, so the lone pair on carbon is donated to the metal, and then metal d orbital is donated electrons donated to the carbonyl pi orbital. This is called back bonding, one type of back bonding. Back bonding we know, right? So in the class 11th or 12th also, when we are reading group chemistry, that time also in many cases we saw that back bonding happens, like right, for extra stability. So in the case of, let's say, BF3 also, right? BF3 also we read that also, right? It has the electrons and it can donate to boron, as the it has electron vacant. It actually tends to complete its octet, so it tends to accept the electron. Okay, so that is the thing, that is a different case, but just to know that back bonding, how it happens. Okay, so this type of bondings are called back bonding. So sigma bonding is from carbonyl to metal, and back bonding is from metal to carbon. Please remember that. Okay. So now the effect of back bonding. We know that, okay, fine, carbonyl and also nitrosyl, cyanide, these kind of ligands are sigma donor and pi acceptor. Okay, that we know. But now what to do with that? Now coming to the now there comes the main important thing, the effect of back bonding. Okay, so let's see what will happen now. So the back bonding, I have previously told you, it is happening from the metal d orbital to the empty pi star orbital of the carbonyl. Okay, so let's say this is the pi and pi star, so it has pi bonds. So pi star is vacant here, right? So metal can donate electrons to pi star. Now let's forget about this organometallic compound, coordination compound. Just forget about those things. Try to remember when we are reading MO diagram in BSc. So in the MO diagram, we have calculated the bond order, right? Bond order was bonding electrons. How many bonding electrons are present in the when we draw the after drawing of the of MO, like N2O2, we have drawn so many MO diagrams, right? So the total number of bonding electrons present minus total number of anti-bonding electrons are present by 2. That was the bond order. Okay. So let's say for nitrogen case, we got that bond order is 3. That's why nitrogen triply bonded to another nitrogen atom, right? And for the oxygen case, we got bond order equal to 2. That's why O double bond O. They exist like that way. Okay. So from the MO diagram, we can have the idea about how the two atoms, let's say the MO diagram of a molecule, we can say about their bonding, how atoms are connected strongly or weakly. How can we say that? Because see, when triple bonding are there, the strength of bond will be much more stronger than single bond, right? If we want to break that, many more energy will be needed. So bonds, from the bond order also, we can have the idea about the bond strength. So bond order is proportional to the bond strength, right? Right? if let's say for example, for a real life example, you are given one stick, okay, one stick, you can easily break that with by putting little bit of energy. But when you are given 2, 3, 4 sticks together you have to break it. So more energy is needed, right? Sometimes you may have cannot break that also, right? So that is the thing. From that point of view, you can from that example only you can understand this matter. So bond order is proportional to the bond strength. Fine. Okay. So why bond order is here important? Because the pi star means it is antibonding orbitals, right? And metal is donating to the antibonding orbital of carbonyl. This is carbonyl, right? So what will happen to the carbonyl? CO bond, how it affects? So as it is donating electron to the pi star, then bonding electrons are same, right? Let's say 2 is here, and previously what was there after before donation? 2 minus 0 by 2, let's say it was 1. Just we are thinking like that way. Okay, so let's say it was 1. Assume that after donation of metal, what will happen? After donation, it is as it is donating in antibonding, and we subtract the antibonding electrons. That time, what will happen? Obviously, bond order will decrease, right? Because we are increasing this term, the subtracting term, right? So if two electrons are donated, right? So 2 minus 2 by 2, what will be? This will be 0, right? So bond order obviously will decrease for the case of carbonyl, CO bond order. Okay. So for to make you understand that only, I have talked about the bond order. These basic things you have to keep in your mind. Okay. Now coming to the another important thing. Okay, from the bond order only we can say about bond strength. Nothing much. Think about it. So for a single bond, this also we know. Single bonds are much more longer, and when double bond is there, the length becomes shorter, and triple bond length is even smaller. So when bond order is increasing, means the bond is like from 1 it goes to 3, like triple bond, right? So bond length will be decreased, right? So it is inversely proportional to the bond length. So that is an important relation. Please remember this. Bond order is proportional to the bond strength and proportional to the 1 by bond length. Okay. So when bond order is increasing, then bond length will be obviously decreased. Okay, fine. Now what? This we know, and here from here how we can actually relate this. So we know for any group that is present or not. Okay, so any this let's say we want to find out for a compound, we want to find out that NO bond is there or not. We have prepared one compound and we just want to know that if any NO bond is present or not. If present, we are confirmed that our molecule is synthesized. Okay. So other factors are there. I am just only assuming this. So to understand this, that NO bond is present or not, we have to go towards the IR experiment. IR gives you the idea about the each and every bonds, how what the strength of bonds actually. Okay, so here we are talking about the bond order, bond strength, right? So we can also from that only we can't predict the actual value, but we can tell that the how the IR data will affect with the back bonding. Okay, so we know for IR or the infrared vibrational spectroscopy. Okay, so nu is vibrational frequency. Nu is 1 by 2 pi into root over K by mu, where mu is the reduced mass which depends on the mass of the compound, and most important thing, K is actually depends on, this is force constant. Okay, this K, the force constant, actually proportional to the bond strength. So when bond strength is increasing, Bs if increases, that time K will also increase. Okay, so how we can relate this four? So when bond order increases, means it goes from double bond to triple bond, like that way. So that time bond strength will obviously increase. How? Bond strength will increase, right? Okay, bonds become stronger and it is inversely proportional to the bond length. Fine. And then as bond strength increases, the K value obviously will increase, and as K value increases, the mu value will be increased. Fine. That's how we can relate this. So mu is equal to proportional to the bond strength. Okay, fine. We have understood how the terms are related. Now we will be focusing on the two things. Okay, two things. What are the things? So M to C donation is there, back donation, and this is also affecting the CO. How? By donating its pi star, so its bond order will be decreased and other things will be affected. But how? So what we are focusing on, which bonds? MC bonds, this is also forming, right? And CO bonds, both has actually opposite effect by the back donation. Let's see. So MC bond means by the donation MC bond present. So the strength of MC bond will depend on what? The MC bond with the back bonding. Okay, because the carbonyl carbon first donated through sigma. MC bond is present there. But when the back donation is there, that time what will be the effect on MC bonds? Okay, that question also can be asked. So MC bond, it was single bond actually. Okay, so when back bonding happens, the bond become double bond, right? So obviously the MC bond becomes stronger. Fine, becomes stronger. Okay, fine. Now stronger means its bond order will be increased from 1 to it goes towards 2 almost. So bond order increases. Fine, that we understood. Now as bond order increases, the bond strength increases, the vibrational frequency we have talked about, mu proportional to the bond strength, so it will also increase, right? And the bond order is inversely proportional to the bond length, so bond length will decrease. Okay, so 4 points are there. You can easily remember this by taking, by knowing this relation only, and how this actually the bond order is related to the bond strength, bond length, and how the after the back donation. Okay, so the back donation, how the MC bond is affected. So how? First, just consider it was a single bond. After donation, it will become double bond. So bond strength will obviously increase, and strength is proportional to the K value, and mu value will be obviously increased, right? So in IR we got the now more value of the frequency. Fine, and as it becomes stronger, bond order will be obviously increased. Fine, and as bond order has been now increases, the bond length will decrease. Simple. Now we will talk about the CO, the effect of CO. How we can know that? So the effect is mainly uh, on the after the donation of to the pi star. We have previously seen that when the electron is donated to the pi star orbital, that time bond order decreases, right? So CO bond order decreases. We have seen that. Fine. Bond order decreases means bond strength will decrease. BS will also decreases. Fine. Bond length inversely proportional. Bond length will increase. Fine. Now new value, new of CO, the bond. Okay, which we are talking about, that bond only, the new of that bond. Okay, so new CO, it depends on the bond strength, but bond strength decreases, so new CO will be, okay, so only bond length will increase. So my advice is, don't try to remember these all things because you can be confused in the exam. So my advice is that you should remember the facts here, how it actually after donation, the pi as it accepting in the pi star, this will happen. Okay, so like that way you try to remember the facts, not the results. Okay, so fine. Now the factors affecting the back bonding. So we know when back bonding happens, what are the results. Okay, now there are some factors which can affect the back bonding. Okay, the back bonding, the let's say the power of back bonding or the donation power of the metal, that can affect. Let's see that. Thinking, right? I am also thinking. So let's just see. So the first one is charges on the metal. This is very important. Okay, as metal is donating, so its charge actually can affect. How? I will be I will make you understand this with an example. Let's say these three complex we have taken. Fine. So both has, what are the difference? It has negative charge, it has neutral, it is neutral, it has positive charge. Fine. Let's just count down their total electron. Vanadium is D3, right? We have to take the 5 electron. Now 12 plus 1, it will be 18 electron. Fine. Chromium 4 is 6, 12, 18 again. Fine. Now here 7, 12 minus 1. So it will be also 18 electron. So see, we can't differentiate here by the total electron, but the charges. The metal center, has some charge because these are neutral ligands, right? So the charge is obviously on the metal. So now we know the difference or the similarities between the examples we have taken. Fine. Now what should we do? See, due to the negative charge, two things are there, two important, okay, important things. So first we will be talking about that when negative charge is there, what can be the difference. We know metal is donating. So if negative charge is present there, so metal has now more electron density, right? More electron density on metal. Let's say for nucleophile, we have read that when nucleophile is neutral, let's say H2O, okay, H2O I have taken, okay, when we take the H2O and similarly when we increase the pH of the H2O solution, we got OH minus. So which one will be good nucleophile? OH minus. As nucleophile we know it donates the electron, it attacks to the through its electron density, right? So as it has lone pair, fine, it can attack. But as it has the extra negative charge, extra lone pair in it, the attacking from that will be more easy and faster, right? It can prone to attack because it is not stable. So due to the negative charge, metal has more electron density and the size of the d orbital increases and become more polarizable so that it can donate in an easy way. Fine. So this is neutral. Let's just talk about the when positive charge is present. So its tendency to the back donation actually increases when we add negative charge. Fine. Now talking about the positive charge. So positive charge has the opposite effect. It shrinks the size of the d orbital, right? As the lone pair of d orbital has gone, and obviously the metal has now shortage of electrons itself. The metal which is actually donating in back donation, it has now shortage of electron. So let's say which I was actually comparing. Let's say here HCO plus we have taken. Here lone pair is another lone pair is present, but can it donate electron? It is not, right? Because it has positive charge. So this is the case. For the simplification, I have taken these examples. So this is the fact here. So this will be now the tendency of the positively charged that complex will be the tendency of back donation decreases actually. Okay. So the order of back donation will be here. Obviously, the negative will be more than neutral, which has no effect, the no charge effect actually, and positive charge has negative effect, so it has the least. Now coming to the okay, now coming to the we know this one, okay, the order of back donation. We know that, right? So from that, which we can conclude. So back donation means I am again writing here MC and here O. Okay. Back donation means from metal to this is sigma and this is pi. Metal to carbonyl and this is donation is towards is pi star. Fine. So when negative charge is there, more electron it can donate, and when positive charge is there, the electron donation is less. Fine. Now, what will be the order of MC bond strength? So, when the donation is more, that time MC bond will have the more double bond character. Means, if the strength of that will be more, when the donation is more, MC bond strength will be more. So, we know that donation order is this. So, MC bond strength will be will follow the same order. Fine. Now, the order of MC bond order. Okay. So we know bond strength is actually proportional to the bond order, right? We have previously read that. So the order is again the same. Fine. The next one, order of CO bond strength. Now we are coming to the CO. Okay. So when donation, let's just think about that. When donation is more, means more number of, this is pi star. So more number of electron is donated in the pi star orbital. When donation is more, pi star has more electron. That means bond strength will decrease, bond order will decrease, bond length will increase, right? So if donation is more, that will happen the more. Okay, that will happen more. So here the bond strength. So if donation is more, bond strength will be least, right? So the order will be reversed. So this for this case donation is least. Donation was least, right? So in this case bond strength, CO bond strength will be more. Okay. So that is the thing, and the order of stretching frequency. So it depends on the bond strength. Obviously the same order it will follow, and the order of CO bond order. Bond order is actually follows the bond strength, right? So it will follow also the again the same order, and the order of the CO bond length actually follows the reverse order. Okay, fine. This from these actually question can ask. They can take many examples with positive charge, negative charge. Okay, so you have to consider that which one can donate in a better way. If any metal coordination complex has 2 minus charge or 3 minus charge, that can even donate, more prone to donate electrons. Okay, so that you have to keep in mind. Just understand, I have previously told you, just understand how the facts are actually related. That will only help you in the question solving. Fine. So in previous years, that kind of questions are actually asked. So that's why I am telling you again and again. Now, one question is there. Which one is more stable and least stable? Okay. We were talking about the MC bond strength, CO bond strength, bond order, etc. etc. Now, which one is more stable among these complexes? How can we say that? Okay. The complex. Complex is formed with any organometallic complex is about MC bond, right? For the metal carbonyl, metal and carbonyl bond. To this bond, metal carbonyl compound actually formed. And if the MC bond strength is more, that means metal carbonyl is stable, right? And from these three cases where MC bond strength will be less, MC bond strength is strength. If high, then more stable, right? And if MC bond strength, if less, then less stable. Because the organometallic compound, or here the metal carbonyl compound, is nothing but the MCO bond. And in which cases the MCO bond is stable or MCO bond strength is more, means it is stable, right? If the strength is more, it can't break easily, right? It is stable, so it will happen. When MC bond strength is more, that time the compound will be more stable. See, you have to just remember the facts, and so that you can, when any kind of question they can ask, and then you can think about the facts and you can solve it. Okay. So now the stability of metal carbonyl is the MC bond strength. I have previously just now told you, just right. So here, what is the options? So one option is that, so here see, here negative charge is present. So here neutral molecule, here two negative charge, there two positive charge, right? So we previously also talked about this kind of complexes. So whenever metal has negative charge, metal with negative charge can donate electron easily. Okay, which result, if it can donate easily, the MC, if it can donate easily, that time what will happen? MC bond strength will increase, right? Or stability increase. Okay, so here negative charge is present here, so donation from that metal will be more. For the second case, donation from the Fe2 minus will be more, so it will be more stable. So more stable will be, I am writing here, more stable will be the second one. That means FeCO whole 4 2 minus. And least stable also they want to know. Least stable means Metal, whenever metal has metal with positive charge cannot donate easily, right? Which result the MC bond strength decreases and stability. Okay, so least stable among these three, least stable will be the complex having positive charge. MnCO whole 6 plus. Fine, these two are the answer. Now, another important thing which can affect the metal carbonyl back donation is the presence of other ligand on metal. Like that, when we are talking about heteroleptic metal carbonyl compound, well, another ligand can be present. So these kind of ligands are called spectator ligands. They doesn't have any uh, direct result or direct effect on the metal 2 carbonyl back donation, but they can affect indirectly. They can affect back donation indirectly. Okay, so two important things are there. So we know the ligands can be three types: sigma donor, sigma donor, pi donor, and sigma donor, pi acceptor. Okay, so whenever sigma donor ligands are present, like NH3, H2O, pyridine, etc., or halogens, that time what will happen? They increases the electron density on a metal, because if the ligands are, they donates the metal, they donates electron pair to the metal. That means they are increasing the uh, electron density on metal, which is for good for what? Good for the back donation. So the tendency of the back donation increases and nu CO decreases. The MC bond strength will increase, but it has a negative impact on the nu CO. Nu CO decreases. Fine. You have to relate it. Okay. Now, if the pi donor ligands are there, like CN, NO, NO, right? They draws, or another CO, when we're talking about a particular CO. Okay. They draws electron density from the metal by extra back donations. So what they happen? They occur. They actually can bond with metal by sigma donation. Obviously, sigma donation is there, but they also can draw the electron from metal pi acceptor, right? So they draws electron density from the metal by extra back donations, which means they are as a result they are actually decreasing the metal electrons, which is the back donation will be now decreased. It has a negative impact in back donation, but it has a positive impact in nu CO, the bond strength of CO, as now less amount of electron will be donated to pi star of CO. So nu CO increase. Fine. Now coming to questions. Okay. So PPH3. Okay. We have just read about the PPH3, but many the phosphorus ligand can be there, and there from these actually questions are asked many times. The donor ability or acceptor ability orders for various phosphorus ligands. Okay, so I will write here. I am not just seeing right now options. So if I consider that the donation, because this is acting like a ligand, right? So the donation ability. So one order I will write here, and please try to note it down or keep remembering it. Okay. Donation ability will be P if 3 or any halogen is present, it has least. Okay. Now P O pH whole. Fine. Now P O M E whole. Fine. Now P pH 3, let's say. Fine. Now PR3. R means alkyl. So the phosphorus ligand which has only alkyl group, they can donate in a better way than these all. Okay. So this is the donation ability. Obviously the acceptor ability will be reverse of it. Okay. So here in the question it is asked that correct order of acceptor ability. Opposite will be the acceptor ability. Okay. For the phosphorus ligand. Okay. What are given here? pH3, POPH3, PPH3, PMH3. We know PF3 is least has least donor ability, so it will accept in a better way. Means it has the highest acceptor ability. So PF3 will be obviously in the first position. So let's see, 1 can be cut out and 4 also. So 2, 3, among the 2, 3, 1 should be the answer. So after PF3, here it is written PME3, but we know that PM3 or PR3, any alkyl chain if present, it can donate in better way. So it can't accept. Okay. So it is a better donor. So this will be the correct option. I have shown you also this one. So after PF3, actually POH whole C is there, then POME3. So here PPH3 is there and PMH3. Okay. So 2 is the right answer here. Okay. Now again one CSIR-NET question, that is the match of the following complexes with their new CO stretching frequency. Okay. So just try to remember when let's say PPH3 is a PR3, let's say I am taking, it is a spectator ligand. If its donor ability is more, what will happen? Will donate in to metal, right? So metal electron density will increase. Fine. Now what is the effect? So if electron density increases, back donation will be more, right? Yes. The back donation is now more. So then if the back donation is more, it will donate, the metal is donating electron to pi star. That means the new CO, the bond strength will be decreased and new CO decreases. Okay. So we have to find out that among the options which has the least value. Okay. Least value is in the option 4. Okay. Least values of new CO. Okay. We got the least value of new CO. Now what we want? We want that that phosphorus ligand which has the highest donor capability. Okay. So we know when alkyl groups are present that time. So here in which option alkyl group is present? No alkyl group is present there. Okay, fine. So okay, forget about this. Now pyridine. Pyridine is what? In one option C, no phosphorus ligand is given. So pyridine is given. Pyridine is simply sigma donor, right? And the PPH3 is there and PF3. Okay. So in the case of PF3, what will happen? Here, PF3 has the least donor ability. So if it is least, the donor ability is least. That time MC back donation will be least and new CO will be more. So the highest value of new CO will be for A. Highest value is C. The 3. 3 has the highest value, which will be corresponding to the A. If it is PH3, if I am considering is a PH3, okay. So it has least donor ability. MC M has now least electron, lower electron, so it can't back donate more. Means you will be more. Okay. So A is 3. A is 3. Only one option has A is 3. Okay. And the least value, which was the 4, 4 will be for D. Because which I was talking about that pyridine is a good sigma donor. Okay. So pyridine is a good sigma donor, which results the it is a good sigma donor. That's why it can donate more electrons to the metal. As a result, the new CO will be decreased. So the least value will be for the pyridine. D will be 4. Okay. So this will be now the correct option. Okay. So 2 is the correct option. Okay. Because the other, let's say other things we want to, let's say for B and C. B has OMe and C has PPH3. We know the donor ability of PPH3 is more than POMe, right? So if donor ability is more, new CO will be less. So PPH3 has the new CO of this and yes, and B has 2 means this one. See, it matches. PPH3 will have less new CO because its donor ability is more, and POMe has the correct option for POMe is 2. Okay, fine. So you can understand that I have clearly told you all the factors and all the things. So I hope you have understood this session and also enjoyed this session. So thank you so much, and uh, thank you so much for joining and keep listening to the session. Thank you so much.